Greetings. Welcome to our 38th episode of the FGI podcast series. My name is Tim Stark, and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign.
And hello, everyone. My name is Jen Miller, and I'm the coordinator of the Fabricated Geomembrane Institute, or the FGI.
On today's episode, we're going to focus on our February 8th, 2022 webinar titled Design of Mechanically Stabilized Earth, MSE, Walls. I'd like to quickly reintroduce our distinguished speaker, Professor Richard Bathurst, who is a professor emeritus of civil engineering at the Royal Military College in Kingston, Canada, where he has taught since 1980. Richard has authored or co-authored over 400 papers in refereed journals, conference proceedings, and research monographs. Dr. Bathurst's primary research activities are focused on the use of geosynthetic and metallic reinforcement in earth retaining wall systems, numerical modeling, seismic performance, and the design of these systems. Dr. Bathurst is also editor-in-chief of the peer-reviewed and popular technical journal, Geosynthetics International, and past president of the International Geosynthetics Society, or IGS. So, Richard, thank you so much for joining us again.
Thank you, Tim and Jen, for having me again, and I'm happy to answer these outstanding questions from my last lecture.
Great. So we have two groups of questions. First is the group that we did not get a chance to answer during or at the end of your webinar. And then we have a second group of questions that were submitted after your webinar in the post-webinar survey. So here we go with the questions that were asked during the live webinar presentation that we did not get to. First question, would you recommend using strength at 2% or 5% or 10% strain versus the ultimate strength divided by a factor of safety?
I would use the 10% strain value to calculate TULT. And the reason for that is a North American standard. And for example, the creep reduced strengths that are used in design are calibrated against the 10% tensile strength in design practice. So that would be my recommendation. I'm not quite sure what they mean by that, by the factor of safety. I presume that's the combined factor of safety for the degradation mechanisms that we associate with installation, creep, chemical mechanisms.
Right. Just to check, Richard, so if you use the strength at 10% strain, do you still apply the creep, the installation damage, and so on factors?
Yes.
Okay.
The problem is if you use the 2% TULT value, then you would be punishing yourself because that TULT value would most often be less than the TULT value at 10%.
Okay, great. Question number 2. Thanks for the interesting lecture. Is the geogrid strain at ultimate tensile strength relevant at the design? The graphic at slide number 30 seems to show that the strength at 5% is important. Is it related to the soil strain at failure?
The 5% strain from a conventional 10% strain per minute tensile test is used as an indicator to show how strain dependent the strength of the reinforcement might be. But it shouldn't be used in design. First of all, it's not related to the soil strain at failure. If you go into the current AASHTO code, what you'll find is that the actual strength and stiffness of the reinforcement, or rather the stiffness of the reinforcement, is based on a creep reduced strength taken at 2% strain in the reinforcement. So the notion of 5% strain using a conventional tensile test is somewhat dated based on current recommended practice in the AASHTO 2020 code.
Okay. Number 3, how does the pullout strength depend on pullout rate?
There's, in some cases, if you pull rapidly on a specimen of geosynthetic in a pullout box, you can get a detectable higher pullout capacity. And it is for this reason that the ASTM standard says thou shalt pull on the reinforcement at a rate of 1 millimeter per minute, if my memory serves me correctly.
Okay. I've seen hundreds of modular block MSE walls constructed to form the limits of stormwater basin where water fluctuates within the basin. Do you recommend against this practice? And I assume that's the fluctuating water.
I think whenever you have a free water level that's moving up and down in front of a modular block wall constructed with dry cast blocks, you have to be a little bit careful, because there's the possibility that you could leach some of the calcium chloride in the cement that's in the block, so that might be an issue. When you have water fluctuating up and down, you could have instances where you have short-term ponding of the water behind the wall, and this means that you could possibly lose some of the soil behind the MSE wall facing. There are some guidelines that have been put out with recommendations for design and construction of MSE walls in shoreline applications, for example, where you may have this type of free water fluctuation in front of the MSE wall. There are other walls that have been built with concrete incremental panels that seem to have performed well in shoreline applications, and I think I may have alluded to that in my first of the 2 lectures. I may have shown some pictures.
Okay. Are CI factors influenced by soil cohesion? Can it be more than 1 for frictional soils?
There's no doubt that if you do a pullout test in which the only difference between 2 tests is the amount of cohesion, then you can get a different result. But it's not really possible to get a influence factor that's greater than 1, because that just means that the failure surface will just migrate up a little bit further from the reinforcement, and therefore the maximum frictional shear strength of the soil will control the behavior of your pullout sample.
Okay, great. Next question. Does the creep test take 75 years minimum? Can't we run it for 5 years and then extrapolate to design life for 75 years?
I don't think anybody's doing constant load creep tests even for 5 years. What we have shown, and the recommendations that are in AASHTO 2020 at the moment, is that creep tests, short-term ramp and hold creep tests, are carried out for about 1,000 hours. And as long as you don't put excessively high loads on these constant load tests, you will be able to characterize the creep performance over any life of the reinforcement based on that initial 1,000 hours. In addition, the standard for establishing the creep, the reduced strength of the reinforcement, is to use what they call SIM testing. This is an elevated temperature stepped elevated temperature testing procedure in which they subject the reinforcement to a constant load, but they increase the temperature around the reinforcement in a chamber around the constant load test. And the thing is, you can substitute temperature for time. So for example, as you increase the temperature, the time to rupture becomes less. And so this is the trick that laboratories use now to make sure that we don't have to sit around waiting for our creep test to continue past 5 years.
Right. Last question from the webinar submitted questions. The design strength of the geosynthetics need to be calculated the same way in terms of creep damage in the case of an earthquake loading. That's a question. Can't we skip the creep reduction for earthquakes as it is probably a short-term loading?
Yeah, this is a strategy that people have used. The trick, though, is what do we mean by short-term loading? For example, if you test a reinforcement at different loading rates in the lab, in air, you can get different ultimate strengths and stiffnesses. So you have to be careful about what is your reference strength or stiffness from a short-term loading test.
Okay, so we're going to move on now to all of the questions that were submitted via the survey after the live presentation. The first one is, do you have recommendations for using freestanding MSE walls to act as rockfall mitigation?
Yeah, that's a good question. In fact, gravity structures that have geosynthetic reinforcement in them have been used for rockfall as rockfall barriers. My recollection, I remember from decades ago, that these type of structures were used in Colorado. I have seen in the literature recently where people have carried out analyses using reinforced structures. They look a little bit like conventional gravity wall structures. It's just that they're steepened up by using the geosynthetic reinforcement. So the answer is yes.
Okay. Second question. Do we typically test the fines passing number 200 sieve of MSE wall backfill? I understand most specs limit the fines to a small amount, but are there instances when we test for plasticity and allow a slightly higher number of fines, say, for example, 4% passing number 200, or up to 10% fines with Atterberg limits, provided the fines are predominantly non-plastic?
I looked at this question earlier and I couldn't immediately remember any specific standards that made this very fine distinction. I think that there are gradation limits that appear in guidance documents like the Federal Highway Administration with respect to putting boundaries on the soil content for use behind reinforced soil walls. A lot of that has to do with making sure that we have soils that are notionally understood to be free draining. I think it's a good idea to not have a fines content with a plasticity index greater than 6. Yeah, that can start leading to problems. So I hope that at least partially answers that question.
Okay, great. Next one. Are there any recommendations that you have if an MSE wall is employed as part of a landfill design?
If you think, usually the MSE walls would be performing as would a steepened embankment around the perimeters of a landfill cell. So what you could replace a shallow steepened embankment theoretically with a MSE wall. Now the advantage of doing that is that you can steepen up at least the inside face of your perimeter embankment, and that allows you to sell more volume to contain waste. So there's no real reason why you can't use them. I think I've seen them, in the literature over a number of decades. So I guess the answer is yes.
Okay. Number 4, when evaluating bearing capacity for an MSE wall, how important is it to maintain the resultant on the base in the middle third? In other words, for overturning.
Yeah. It's not important. Firstly, overturning is not a failure mechanism for MSE walls because MSE walls are very flexible. The notion of overturning is something that we have inherited from classical retaining wall practice for gravity structures and for L-shaped or T-shaped cantilever walls, where this is a potential failure mechanism. So the mechanism doesn't exist, and therefore this middle third business really doesn't need to be taken seriously.
Okay. For wrap wall facing, what is the expected life of the wrapping, and can one expect over 100-year life? Are there any tests that might estimate life of the exposed wrap to the weather elements?
The exposed wrapped face should only exist, in other words, be exposed for temporary structures. Otherwise, if you have a wrapped face structure that is designed for a longer life, you have to coat it. So you may use a shotcrete material, you may use asphaltic materials, and there are a number of walls that have been around for decades. There was a case study recently in a journal where they went back to a wall that had been constructed more than 25 years ago, and they looked at the facing, and they determined that the original asphaltic coating had adequately protected the underlying wrapped geosynthetic.
Right. Richard, another question on the CI coefficient. Could geogrid joints create soil arching during pullout and sands? If so, can CI be larger than unity or 1? Does soil cohesion for reinforced on-site soils, for instance, have any influence on the CI factor or coefficient?
I guess there's sort of two questions there. First of all, the notion that you can have this type of arching, that might happen, but as I said before, all you're going to do is move the sliding surface on both sides of the reinforcement up into the soil where the arching effect has not penetrated. So I'm not sure that notion is true. And again, I think the influence of the cohesion, whatever it is, if it's there or not, it will automatically be captured by the magnitude of the pull-out resistance that you measure in the lab using a standard ASTM pull-out test protocol.
Okay. Number 7, would you compare and contrast MSE design standards with IBS GRS, and that's integrated bridge?
Yeah.
Okay. Design standards.
Yeah, definitely there's a bit of a difference because the IBS GRS system is a heavily reinforced composite reinforcement granular mass slab. So it really is an integral system. Ideally, you would expect that in the limit of the design methods that we currently use for MSE walls that are typically higher and not as heavily reinforced, that those two methods would come together. There's an indication that they do, but basically the GRS structure is quite a bit different from MSE wall structures. The other thing that's different is the deck bearing. You know, in those GRS walls, they have a large reinforced concrete deck slab that sits directly on top of the reinforced soil mass, and that puts quite a bit of load on the reinforced soil mass, and that has been a challenge in conventional, simplified, and stiffness method calculations to correctly estimate what the additional load in the reinforcement layers will be because of this surcharge. The GRS methods that people use, it's sort of an off-the-shelf boilerplate type of approach, which has that built into their design method. And so, you know, that's certainly an advantage to use their design method for this particular class of reinforced soil wall systems.
Right. Okay, number 8. If you could speak to the appropriateness of using traditional bearing capacity and settlement calculations, which are based on a rigid foundation, to a flexible reinforced mass of an MSE wall or reinforced soil slope, but those are really two different animals, but I'll let you handle that. Is there a better method or appropriate factors to apply to better represent the bearing capacity and settlement of the flexible mass?
You know, the foundation soil is really quite stupid. It really can't tell what is applying the surface load at the top of the foundation. So I would just recommend that however you calculate bearing capacity and settlement, assuming a flexible surcharge load, you know, of finite width, just use the same methods that you find in textbooks and have been used for a long time. The physics of the problem remain the same.
Okay, number 9, and there's only this and one more. Question was just for more discussion on leveling pad and first element. I see them often be an afterthought by some designers who rely on the block wall type manufacturer software and do not really check overall stability. Those checks were touched on in your presentation, and you noted several times they need competent designers and experienced contractors. The lack of those two items often creates a black eye for MSE structures.
Yeah. Yeah, you need to be careful when you use vendor software, because first of all, a lot of them are black box. What you want to use is generic software that allows you to independently check design outcomes. And there are some that are out there that allow you to do that. And I might also add that if you use a vendor software and something tragic happens to your wall because of inadequate design, you know, you're responsible. Okay, you can't blame the vendor. Now, it's true that some of these packages they don't check for overall stability. I think I understand that question to mean, you know, global stability and compound stability. So you have to do those calculations separately using other software. For example, software which has been modified, you know, slope stability software, which has been modified to capture the additional benefit of the reinforcement itself. The footing itself, yes, you have to be careful. You have to treat the footing as you would any footing below a continuous strip loading. And equally important is you have to build those footings carefully. They have to be of sufficient strength and stiffness, and they have to be as dead level as possible, because any bumps in the running length of the wall, that will chase you up that wall. And sometimes what will happen, you'll see cracks propagating up the wall, which is bound to make people unhappy.
Yep. Okay, Richard, last question. Number 10, how effective are MSE walls stability in saturated soil conditions below phreatic line compared with gabion wall design?
Yeah, this question, I understand gabion wall design to mean these gravity structures, which are built with large, for example, meter wide blocks. They stack them up, but they're basically a narrow pyramid shape. And those structures are quite common. The inside of those gabions is, typically a very coarse grained granular material or slab rock or something like this. And then behind the gabions, they will often put a geotextile to prevent any retained soils from washing through. For MSE walls, I don't recommend these structures being built with the anticipation of a constant phreatic surface intersecting the face of the wall, and preferably not intersecting the reinforced soil zone. This is bad practice. You got to make sure that any water that comes close to your reinforced soil mass, including the facing column, needs to be intercepted and directed away. Otherwise, this can lead to long-term problems.
Right. Okay, Richard, that's all the questions. Thank you so much for joining us again. And that's all the time we have. If you have additional questions or would like additional information, you can contact Professor Bathurst at bathurst-r@rmc.ca. Bathurst, BATHURST-R@rmc.ca. Or you can email the FGI at fabricatedgeomembrane@gmail.com. You can download the webinar slides and listen to Professor Bathurst both webinars on MSE wall design at fabricatedgeomembrane.com. So, Richard, thank you so much for joining us again. And everyone, thank you for attending.
Thank you all again.
Thanks. Bye-bye, everyone.